Hey, welcome to another Toolbox stunt rigging Toolbox talk. I've been working on some trailer bits. Anyway, this is the bazillionth time I've redone this because there's so much information. I'm trying to frame it and be able to cut back and forth everything. This is about bollards and a way to avoid the so known circus ties and the strength of your hitching and the use of your rope without destroying it. As most of you know, you can put an eye in the rope and pull it to, with our new tester, we've proven that we get to 3.7, 3.8 tons for 6mm Samson before it breaks. And that's with a splice in it. Minimum braking strength, MBS, according to the manufacturer, is 3.3 tons, so 3,300 kilos. We've proven all that's correct. We now have a great baseline. In our business, what happens a lot of times is people will run a route, run all their performer lines, and they'll come back to whatever it is, whether it's a hand pull line, a ratchet, whatever the engine of choice is. They'll come back to a carabiner, and they will proceed to wrap and hitch to that carabiner in several ways. One's called a tiger tie. I generally lump them all as circus ties. There's some form of wrapping around the carabiner, wrapping around the standing line, putting half hitches in, and then securing the end of the half hitch on the bite, the loops, into the carabiner. You've seen us test those before. And I hate them. They are a lazy excuse to have 10 extra meters of line in the air hanging on this attachment in case, God knows, you need to extend or bring in, but in case mostly to extend. So you leave 10 meters of extra line up there. And you've got this hank of shit floating in the air attached to a carabiner with whatever you're doing, whether you're hand pulling, ratchet pulling, whatever, okay? I mean, it's whatever your engine is. So what happens is we've tested these various circus ties and they don't go over a ton, okay? Even with the new dyno, and I was being generous last time, they were a ton to 1.1. Right now, any of the circus ties is good braking strength. Braking strength is 1 ton. Okay, so what you've got is an MBS rope of 3.3 in your system to your performer, and you're coming back and terminating it with a 1.1 or 1 braking strength MBS. So it's 30% of the braking strength at your carabiner. So the solution to this is either to splice it and eye it and make a service loop in your system, which is a bite with a floating pulley that is halfway to your height reds, so that you can extend or retract your performer 6 meters, say it's 12 meters high, 6 meters in either direction, and you never have to change your operating station. You have it on a clutch, it goes through a pulley, it goes to your bite. Your line comes out to your performer, goes up through the pulley, through the bite, and then off to your performer. So this bite now can come all the way to the floor, subtract 6 meters, go all the way to the perms, add 6 meters from your fixed point. That's my usual solution. It means putting in 2 extra pulleys that don't really matter, okay? And it makes life really easy. It gives you options for other things. A lot of people don't do that. A lot of people just run their performer line straight through, down off that head block pulley, and tie in. And then they leave 10 meters of line all wrapped up and clipped into the carabiner, and then taped with PVC tape to the running line. Okay, that we know is good braking for 1 ton. So it kind of defeats the whole purpose of running really nice Samson 1/4 inch Tech 12 of 3.3 tons braking minimum in spliced condition. And on top of that, when you have it tied around your carabiner and say you go, okay, a gold tail drops 500 kilos, 5 times 100. If your performer is 100, it's 5 times. If your performer is 80, it's 5 times. It'll be 400. But so you're at half of your braking strength, and then you suddenly need to let out 5 meters. That piece of line that has been caught in the carabiner and wrapped around is going to show wear and be out in the middle of your system now. Okay? It's going to be 5 meters, 10 meters out in your system. And it is a compromised piece of rope. So that really kind of just totally defeats all the purpose of doing this. So hence the bollards. This is part of a Jack Rubin bollard. Everybody knows these. They have a top plate that's bent. The problem is it's hooked to a carabiner. You have to undo it, open it up, wrap it, and you tie to a funny little hook that's on the side. And what happens is, because it's a single 35 millimeter drum, it breaks the line at about 1.8 tons, okay? And they've got a working load limit of 1,100 pounds, because it's an Imperial American product, which is 500 kilos. So that's we know they break at 1.8, so that's basically 50%. Okay, so you have a 2-to-1 safety factor with 6 mil on this, okay? And that seems really stupid, because you're using 3.3 ton MBS rope. So we started trying to play with various bollards. We machined little plates. We machined little bits that were inset and pressed in. This model, before it bent with 12 millimeter, and the tie off here on a single got to 1.8 tons. Okay, so 1.8, half of that's 900 kilos. That's pretty good. That's double what this one's rated at 2-to-1. Okay, but it looked like that. And the rope gets shit and gets destroyed. So after a lot of thought, I started doing something that's called doubles. So we made another plate to go. So we went through testing and breaking all of those. Then we went to, it's always how you manufacture these things. So then we welded larger diameter, because remember, the radius plays a big part on tech and its bend over radius. So we went to 50 mil. We pressed them in and welded them. Okay, these pulled to 2 tons, no problem, with 12 mil, and they're doubles. And so I was looking for a way to tie off, and I put these standoffs. You'll see these in arborists, you'll see these in boats, see them a lot. But for our application, I hate them, because I call them the sticky outy bits. They hang up on everything. They're a fucking nightmare. So what's the solution? Well, then we produced this model. It's double drums that are 50 mil. I've machined them so they have a end on them. They can't slip over the end. It's in 15 mil alley, and they are inset and bolted, okay? So we use these. Now I'll give you the specs ahead of time, because what you can do is it's offset so that the hole for the carabiner is on one side of this bobbin. Okay, so if you wrap from your performer line around that side and start there, it doesn't cock in the air, it pulls straight through the carabiner. So you do a wrap around each, you keep wrapping, and then you throw half hitches around these bobbins, and then you take the end and put a bite in your carabiner to lock it off. What you will notice is that as it tensions over a ton or ton and a half, it does slide and stretch around these drums. It gets significantly tighter, but with 2 of them, it can spread and not tighten just around one. It starts pulling from the other. Okay, and that way it tightens up on both drums. It's not just a single point, and it holds very nicely. We tested these, and with the new dyno, and I'll put one sample up now, and you'll see it. We got to 2.8 tons. 2.8, 2.7, 2.85. We had a couple of 2.9s. But let's call it 2.8 before it broke, and I'll show you how we broke it. We wrapped it on the bollard. The bollard's attached to the dyno. We put the loose loop, 40 mil loop around the end, and we pulled on it until it broke, okay? And we marked a random point in front so we could watch how much stretch and how much, once you get over a ton and a half, how much it tightens, because it's loose, and as you tighten it, it gets tight, so it gets smaller diameter, so it takes less space on the drum, so it kind of slides around the drum, but it tightens up on the back drum as well, so it's not just constricting on the front drum. Okay, and that would break at 2.8, 2.9, 2.75, 2.7, okay? And I'll clip in one of these, and we can look at it, and then I'll go into what we did next, all right? So that's a bollard. It's about 800 grams. After we've done all this testing now, I know I can put it on a diet. I can probably get it down to around, this one's 450. I can probably get it around 500 grams. I can go to a 12 now on the plate, not a 15. I can thin the wall down on these bollards, the actual drums, and they'll be fine. So I can pull a couple 100 kilos, 300 kilos, or 300 grams out of this and bring it down around 500. So watch this one, you'll see the break, okay? And then we'll discuss it. Hey, so we're back again. You've seen the break, which I take up in steps because I want to see where it's going. I just don't want to hammer it straight away. So we went up in steps, and you also saw the video of it breaking on the front of the bollard. So now that we know we're getting 2.8, 2.9, 2.75 out of these, well, where is it damaging the rope? Because the whole point of this is so you don't fuck your rope up. Okay, so what we do then was we wrapped these the way we just did, took them up to around, and remember, we're taking them up to about 300, 400 kilos, 300 kilos generally, so the line is tight and not just going into slop, okay? And that way I can read it from there. So we take it up till it's tight. I put a tape mark in the line where it comes out of the front of this bollard out here, and we pull it, and we've actually pulled it to over 2.5 tons, 2.4, 2.5 tons, 2.6 tons, which is almost breaking, and held it there. And you'll see that on the graph, the stepping. And then what we did after that, we stepped it, and you'll see that on the graph. And then we took that piece of line, the very same line we had just used, we take the part where it's taped and where it went around the bollard, and we splice an eye on that section so that we can put that section in the brake tester. And we can test if that part of the line is damaged. And lo and behold, with the double bollards at 50 mil diameter, you will see the results. We were over 3.3. We were at 3.4, 3.5, 3.6. 3.4 was the lowest, so we're still at MBS of 3.3. I mean, default is MBS says 3.3. Okay, so we're over the MBS of the line when this bollard section is put back into service. Okay, and you'll see that because we'll do a brake test on that, and then we can come back to it. So you'll see I step it and hold it and just let it sit there at 2.4, 2.5. I'd have to look at the graph again because this is about the 10th time I've cut this, and it just makes no sense because there's so much information. I'm trying to do it in sections now so I can edit it better. And once you see how we've held it, you can read the numbers, and I'll go through it in the end. And what we do is then we take that off and break it and see. So watch this and you'll see it. All right, so now you've seen us step it up and you've seen us break that same piece of rope. And I'm only putting one example in. We did like 10 of each. It's just very tedious. It takes a long time because after you've got enough rope to do the bollard test, then you have to re-eye the other side and actually both sides because of the length of everything and put that used section, which is normally a little fuzzy, and we have seen individual strands in each of the 12 strands breaking, meaning there's hairs broken, not full strands broken, because it's 12 strand hollow braid. So each strand is, there's 12 strands, but in each strand there's multitudes of strands. And you can see it starts getting fuzzy because it's been pulled within an inch of its life. As it flattens out across this radius, near limits, it starts breaking. The outside curve is under more tension than the inside of the radius, so it starts pinging little fibers. So you could see it, and I have my magnifying glasses, and I would fully examine each section, and I saw a ping here and there, okay? Nothing severe. I mean, I've seen it way worse, but nothing that qualifies as a broken strand, just fibers within individual strands broken. So it looks a little fuzzy. And then when we broke it, we were well over 3.3. We were breaking at 3.7, 3.8, 3.6, okay? Well up there on the normal MBS of this line. The lowest we got was 3.4 tons, and that's above the 3.3 MBS of the manufacturer. So we can deduce from these numbers, which we've done over and over, that by tying it around this double bollard, we have not damaged the rope when we pull it to 2.4, 2.5 tons, okay? By putting it back in line and checking it again against the dyno results of what we know it breaks at. So when it's on this, you put that section of rope back in the system, it still is at MBS of the factory, okay? So in other words, the bollards are a success. Now, there's some things we can do. These are the prototypes. I've got made them. They're all the same. And we did this because it's easier to produce. Welding takes too much time. The sticky outy bits are useless. This is just chuck it on the lathe, make these, make the base plate, drill it, thread everything, bolt it together. And these are 1/2 inch or 12 millimeter, however you want to look at it, stainless steel A4 fasteners. And they have a couple of ton shear force on them. So that's in straight shear. And with the plate they're on, the force is trying to bend it this way. So it's not in direct shear. So they're going to hold well over what the actual aluminum plate is. And I can look it up again, but I did when I designed this, I did all of the numbers. And the nice part about A4 is it does bend. So if anything was going to happen, I could see it bending before it breaks, which is why I use the A4. I don't see any increase in distance on these. They are parallel. So we know that this piece is not bending. So we can deduce that this will hold 2.4 tons without damaging the rope, and you will be able to use it. So now if you are a wad of shit hanger and want all that extra rope in there because you're too lame to put a service loop in it, you can hook your rope to this, leave your X number of meters hanging there, and it will be at least 2.4 ton worthwhile. And when you put it in the system, it won't hurt anything. Now, I've kind of downrated it because at 2.4, I just call it 2.2 now. It's 200 kilos difference because 3.3 tons is 3,300. 1/3 of that is 1.1. 2/3 of that is 2.2. So that's 60% working load on this bollard of 3.3 MBS line, okay? So you still are doing far better. You're double the braking of this, and you're basically over 4 times the working. This breaks at one ton. So your working load's half of that, 500 kilos. If you could work at 2 ton on this, or 2.2 ton, you're 4 times better on this working load limit on this. Okay, so therein lies the differences on working load and braking load. But we can also, when we derate from braking, knowledge of braking load, we're still higher than the carabiner tie. The carabiner tire brakes at 1 ton, working load limits 500. That's 2 to 1. This says 500 kilos, actually, yeah, 500 kilos, and it's working load limit, and I can tell you right now, it doesn't even quite make it at 2 to 1. This one, we already know was 1.8 tons on a single bollard, but we know these now are at 2.2 working, okay? And at 2.6 or thereabouts, 2.7 braking, 2.8 braking. So there's a lot more room to play with and a lot more design factor. So now your working load on the carabiner tie was 500 kilos. Your working load on this is 2.2 tons. Okay, that's over 4 times as good as tying it there, plus you're not damaging the rope. Okay, so that's what we've done. That's what you've seen on the tests. So these are going to be a product, I'm going to use these myself. I've given them to some people to play with to see if the weight's really that big a deal. I'm going to throw some more on the lathe and chuck them up and thin them down a little bit, put them on a diet. But we know what they do, and I'm going to also test a 12 mil plate here instead of the 15 because I don't really think we need it at these levels because we were getting almost over 2 ton with just the 12 mil, and the bobbin is what makes the difference. And plus we're not setting them in. Notice this was recessed in, pressed in, and before it was bolted, and now they're basically a couple thou inset to allow for the radius to be smooth and not have any edges on it, and they're not inset any more than that. So what we have is the whole bobbin trying to bend this plate instead of half the thickness, it's the whole thickness. And this was half the thickness of 12 mil, and this is the whole thickness of 15. So we're going to make it with a 12 mil down here and retest. But that's kind of not a big deal to me now. We know what we're gonna get. I can truly say because of the difference of the way the bobbins are. The bollard, the double bollard without sticky outie bits, not welded, nothing, just bolted bollards, which is a lot of the arborists use them this way. There's some cool products out there like this. And you can always change your bollards. You can always change your backing plate. You can always, if you damage it, shit gets ruined when you're dropping big, heavy objects. And they use these a lot as braking mechanisms. So these function, they work in their designed way. You can utilize your rope. You can have extra rope on them. You're never going to damage your rope. 2.2 tons working load limit. And yeah, with the new dyno, we were able to really get into all these details and know it. So, you know, not one of them broke below the MBS. Not one of them. Okay? Even when we were in just a bollard configuration, they were within 500 kilos of the spliced minimum braking strength. Okay? So we were at 2.7, 2.8 braking on the bollard, and that's pulling it flat over these drums, not in an I-splice. An I-splice minimum is 3.3, we're at 2.8. So by derating these down to 2.2, I know we're more than safe because at 2.4 we can do it all day long and we don't damage any rope. So now if I say it's 2.2 working, we're plenty good, and that gives you far more design factor if you're going to use a way to tie other than put an eye and a service loop in. All right? So that's what we've done today, and I'm going to leave it simple because I was getting complicated on a lot of the other ones. But we've proven it with our new dyno, 1,000 times a second sampling. We've proven what the circus ties do and when they break, so we don't need to bother with those, and we basically improved on the situation by having this, and the only thing I could do now is put it on a little bit of a diet. So there we are. That's about bollards, circus ties, and your 6 millimeter or 6 millimeter / 1/4 inch Samson Tech 12. and working without service loops and without splices and just trying to use it as a bollard. So we have these. We're going to decide how much they're going to cost to make. I have to look through the time and effort. The materials are not that expensive, but it's the time to spin these off and cut them out. And it's also how much people want to use them. Most guys are just like, oh, that's how we do it. We tie it around the carabiner without knowing the math. I don't expect to change the world here, but I know I use these. I used my stainless steel ones before, but I'll use these from now on and get rid of my stainless and use my aluminum ones, or aluminium, however you choose to pronounce it now. So that's it for today's Toolbox Talk. Hopefully it's simple enough. We only did a test one on each of these video to show you, because otherwise it's just tedious as fuck. And we put a piece of board up behind the dyno so you could actually see shit breaking instead of seeing it against the wall, which with the heaters and stuff there, it kind of gets to be hard to see. So we tried to make it visually okay for you. You can freeze and look at the numbers. I put on a couple of screenshots of the braking and stepping, and you can look at the numbers on the bottom right-hand side. You'll see the time factors on each of the steps. You can't really navigate through them, but you'll see how I brought it up and stepped it, and you'll see what we proved. Okay, so that's us. Be safe out there. Know what you're doing. Know the difference of braking strength versus working load, and act accordingly. Okay, and try to operate safely, folks. That's all. Take care.